Hi, welcome back to our machine learning course. Now we've built a number of convolutional networks. It's time to see whether they have actually learned something useful. And we can do that by interpreting the model, by looking at particular outputs or the weights themselves and see if they respond to anything we can recognize as being useful. Right? One thing we can do is to observe the intermediate feature maps. Remember that when we are building a network, we take an input image and we feed that to a convolutional layer. That convolutional layer has a number of filters, say 32, and each filter will run over the image and give us a certain output. Right. So this filter will run over the image, change the input image in some way, and then the next filter will do the same thing in a different way. And so we'll end up with a tensor which is more or less n by n, maybe like n minus 1 by n minus 1, and then has 32 output channels, one for each filter. Now what we can do, we can look at these activations, and the way we do that in practice in PyTorch is by creating a hook. A hook is a simple function, and we're going to hook that to our convolution. Remember, our convolutional layer is also just a function. And so we're going to add this hook to the function so that we can intercept the output of that function. So we're going to attach it to a module, to a layer, and then we're going to take the output of that layer and we're going to detach that and store that into a global variable called activation. Right. So first of all, we're going to take a model, we're going to take a particular layer in that model. Since this is a ResNet, these layers, or the parts of the convolutional part, are called features, and we're going to choose a particular layer in that array of features, and then we're going to register the hook here to that one. So here we're going to attach the hook to that convolutional layer function, and when we then take a particular input image, we're going to pass that through the model. When that image passes through this layer, the hook is going to store the output in this global variable called activation. And this will be exactly this output layer, this output tensor. Right? I'm going to return that when I'm done. Okay. And so now we can choose different input images, feed them forward, and we can look at the activations. And again, we'll get 32 responses if we have 32 filters. For one example, this cat, we take the first layer, first filter, and we're going to see what is this filter responding to. And what we can see is that it seems to respond very much to, can you see it? Sort of horizontal, well, vertical lines basically, right? It responds mostly to vertical lines in the image. And so the same filter will do the same thing no matter what the input image is. It will always respond to vertical images, right? Vertical edges. So if you go to this dog here, then again we will see that what it responds to are all vertical lines that occur, well, vertical or almost vertical lines in the input image. Right? Now, this is just one filter. We can also look at all the filters in a single layer. And if we do that for our cat image, we can see that these filters, they learn sometimes very similar, but sometimes also very dissimilar things. The first two look, for instance, very similar, but it could also be that they're similar for this input image. It can be that although the first two here on the left look very similar, they may look very dissimilar if there was a different input image, right? But we also see that, for instance, this filter here and this filter here look very different, right? So they respond to very different things. This one seems to again respond to vertical lines, while this one seems to respond mostly to light colors. Remember when we look at our cats, we have white colors in the background and on her face on the left side on the bottom. So this one, the second filter here, seems to respond mostly to light colors in the image, right? Other ones, this one seems to be reacting even more. Like this one here, seems to be responding even more to purely white colors. This one seems to respond a lot to the eyes here, right? And we can see that all these different filters respond differently to different things in the image, right? And that's what we want. We want every filter to learn something unique so that we can extract a set of useful features, simple patterns, from the data so that we can afterwards identify whether it's a dog or a cat. This one, by the way, it looks a lot like it's detecting eyes already pretty clearly. Okay, that's the first layer. We can also go to the next layer, and the first thing we'll see is that the images get a little bit more fuzzy, and that's because also the resolution changes. Remember, we are passing through a max layer, so if we had n by n images here, if we go through a max pool layer, then this is going to be n divided by 2 by n divided by 2. So we're going to lose a lot of resolution, and we see that happening here. And by the way, every one of these filters in the next convolution layer combines all the information of all the other features in the previous layer, right? So this one feature here learns how to combine all the information, all the activations of the previous layer to see if by combining those things, it can find new patterns that are useful to make the right prediction. Well, in principle, it will adjust its weights through back propagation so that it will respond more actively to something that's useful to lowering the loss, right? And we can also see that, again, some of these guys are very responsive to eyes. Some of them were very responsive to the forward, the background, or particular colors in the image. Some of them, like this is very interesting, they respond to all kinds of small edges, no matter where they are. Like this one seems to combine edges that are horizontal or diagonal or vertical, and combining all of them in the same input image. It's very interesting. This one also seems to do that in a different way. Yeah, and you can see that all of them, they kind of respond differently. This is peculiar here. There's this point that comes back here and here. Maybe there's something in the input image that causes that. Right. So that's it. And another thing we can see is that some of these are black, right? And this can happen typically this early in the network. It typically means that we're dealing with dying ReLU. Remember our activation function. So if we have in and out, ReLU will output nothing until we have the 0 point, and then we'll output the same input as output after this value 0, which means that if you remember looking at the gradients, the gradient of this is going to be 0 here and 1 here. And so this means that if of all the inputs that reach this particular filter, if they are very negative, then the derivative is going to be like the particular component of the loss is going to be also 0, which means there's no gradient to pass through, and this filter might actually die because of this. Right? Okay, so that's it. Let's go deeper now. Layer 5, layer 6, the third convolutional layer. So here again, the resolution gets smaller. We again see some filters responding very particularly to eyes or ears. Yeah, some of them just pass information through. Some of them, yeah, seem to again combine information from others into one filter. This one seems to be responding very much to, I don't know what it is, anything that looks like even slightly circular. Yeah, so we can see again that all of these respond very particularly to certain aspects of the input image. Also here we see a lot more missing filters as well. Layer 9, again, now our resolution gets really small. Maybe it's only 16 by 16 anymore. And we can see it gets more and more abstract. And since every filter combines all the information of all the other filters in the layer beforehand, and now we're combining information out of 64 filters into every new filter, these things get very abstract. And so at some point, they're just responding yes or no to certain patterns existing in the image or not. We can see there's a lot of repetition again. Some of them look very similar to each other, and some of them again are black. Now, deeper in the network, if you have a filter that's non-responsive, it can be that this filter is only responding to certain classes in the image, right? So for instance, if you look here at input of a cat, and this is an input of a dog, we can see that, for instance, this one responds to the dog while it was 0 for the cat, right? And vice versa, like this one as well, responds to the dog but does not respond to the cat. Right. Anyway, so what we've seen now is that the activations, they seem to respond very nicely actually. So we see eyes and ears appear, we see colors being, we see filters being active for certain colors. We see combinations of features that are important, like the face of the shape of a face and so on. So we see those filters are actually learning something useful, and that helps us to, well, trust those models more, that they learn something useful. One thing you can also see here is that deeper network, some of them look very similarly, and this may mean that we might not have needed 64 filters so deep in the image. We might have gotten away with a few less, maybe. But that's something we have to try to see if that's true. Okay. Yeah, so from this we learned that these convolutional layers, they learn spatial hierarchies of patterns. We saw that the first layers only learn very small, like vertical lines or particular small aspects of the image, while deeper ones respond to eyes or ears or noses in the cat. And then by deeper layers of abstraction, eventually it becomes very easy for the model to identify whether it's a cat or not, right? We even saw that some filters will only respond if there's a cat, or only respond if there's a dog, right? And so by doing that, it becomes very easy for the last layer to then identify, oh yes, this is a cat or this is a dog. Okay, another thing we can do is to visualize the filters. So remember in the beginning here, when we had this drawing of our model here, yes. We visualized only the activations, but we can also try to see whether we can look at the weights of these filters I learned here and see if we can visualize that in some way. Right, what we'll do here. The approach here is very, very different. So we're going to start, first of all, by taking, well, look at the filter in isolation, right? So we have a filter here. It's trained, it has particular values. We're going to freeze those values, we're not going to touch them. And we're going to see, okay, what input image would this filter respond to? We could actually visualize those weights, but they won't tell us much. It's just a 3x3 matrix, right? Like this guy. We won't see much. Well, this happens to be clearly sort of an architecture, but yeah, in general, we cannot sort of see very easily what the filter does. We can try to visualize that by taking a random input image, it's purely random noise, feeding that through the filter and looking at the activation. Now, if the activation is high, it means that the filter is responding harshly to the input image. So if an input image would have patterns like vertical lines that the image responds to, then activation will be high, right? And the same way, if we have things like horizontal lines in the image and the filter responds to that, and activation will be high, then that means that the filter is responding to horizontal lines in the image, right? And so we can actually learn this. And so we try to visualize this here. So we start with a purely random input matrix, which is random values. We're going to feed that through the kernel, and we get kind of a low activation from that, right? So the next step I will do is we're going to compute a loss to train this input matrix, right? So it's very different from before. So we're going to view this input matrix as a set of weights that we can learn. And we do that by first assigning these as weights, right? Telling the optimizer to optimize these weights, feeding that to network, taking activation. From activation, we take the sum of all the activations, and we're going to feed that to a loss function. And then we're going to take the derivative of this loss function with respect to every value of the input matrix. Right? And so we're going to tweak all the weights, all the values of the inputs up or down a bit so that the loss goes down. So if this particular input value was high and the loss and the output was too high, then we'll decrease that value of the input and so on, right? And so we're going to do this over multiple iterations, and so what will happen will be something like this, where from this random activation, every step we do, we're going to change the input image until it kind of converges to some patterns that the kernel responds to, and the activation becomes very, very high, right? So this is just a caricature, right? So this is not actually what's will maximize this activation, but we'll see that the idea here is that, okay, horizontal lines seem to make this kernel happy, so the kernel responds, well, the activation will be high, and that will mean that that this is a kind of input that the kernel responds to. So that's a kind of pattern that the kernel is looking for. Okay. Good. And we call this a gradient ascent in input space. So basically, we're doing gradient optimization. So, but while we're Normally we try to minimize the loss. In this case, we want to maximize activation. So it's instead of gradient descent, it's gradient ascent, and it's not gradient ascent in weight space, but gradient ascent in input space in the input pixel values of the input image. Right, so now that we know the theory behind it, let's see how we can implement this exactly in PyTorch. We start by first creating a random input image, just uniform values randomly, and a bit normalized, right? And then we're going to convert it to tensor. We have to transpose because PyTorch tends to like the channels in the first dimension. We're going to move that to the GPU, and we're going to tell it, well, this input tensor has gradients, right? So we're going to learn them. And then we tell Atom, our optimizer, to optimize the weights in our input image. Okay. Then we're going to take a number of iterations. We're going to attach a hook to my layer. And every time that our image passes through the model, we're going to compute a loss that's based on the activations. Now, Atom wants to minimize loss, so I'm going to just minimize, I'm going to do minus activation, right? I want to maximize activation, so I'm going to minimize the negative activation. And this is just the sum of all the activation values for that particular filter, right? So if that's not clear, what we're doing actually is we take all the activations, because a filter has, well, a layer has a lot of, we can only attach a hook to a layer, but we only want to measure activation for a particular filter. So if you want to filter 16, for instance, we're going to extract the output of filter, the activations of filter 16, right? And we take the mean out of all of these. So activation is my entire tensor. I'm going to extract the 16th value here. This is this output, and then we take the mean, and that's my loss, right? And then I'm going to optimize my loss function. I'm going to optimize the weights of my input matrix, right? So I'm going to compute a loss based on this, and then we're going to compute a gradient with respect to the inputs x, so we can optimize those weights so that next time they will respond more actively. So this guy becomes hotter, has higher values than before, right? And then we'll do that for a number of steps, and then we can see what the input image is like. Okay, so now we can see what it actually look like. So if this was for our 4 convolutional layer network. We can see that some of these respond to certain colors, so some of them respond very strongly to green or red or black. You can see some of them also respond to lines. This one responds to diagonal lines. This one responds to lines in the other direction. This one seems to, that's more horizontal here, and this one looks more in this direction again. You can see some of them also have a bit more grainy character already. And so, right? That's the first layer. First layer are always very simple patterns like colors or horizontal or the other lines. Deeper network, it gets a little bit more complicated, so we can see, yeah, it's hard to have a very good view here, although this is very interesting here, the way it responds to things. Yeah, other may respond more to certain combination of patterns, although they also seem to be pretty similar. You can also see that this filter here is trying to do 2 things at the same time. It's trying to, yeah, it might actually be responding to, I don't know, horizontal lines and other things at the same time, or equally likely we didn't do enough iterations and this particular input image hasn't converged yet to one particular output, right? It's also possible. Even deeper, it gets more interesting, so we can see like circles appearing. So this guy may actually be responding to circles in the images. Yeah, here we see also some round shapes maybe. Yeah, so on this scale it's a bit hard to see a lot of information, but we see that deeper in the layers at least, they respond to more sophisticated patterns in the image. Right? Now, this particular method, yeah, requires a lot of data to get it right. So, in our cat and dog data set, it's not that large. So, we're going to repeat the exercise on a large data set and a larger model. So, we're going to do this on the VGG16 network. So, this one has a lot of convolutional layers, as we saw before. This is pre-trained on ImageNet. 1000 classes, version 1. So ImageNet has multiple versions. This is the original version. Later versions were cleaned up a bit more, a bit smaller, but more clean. This is the original ImageNet dataset for which we have the weights. And we're just going to take the model, pre-load those weights, and we're going to visualize those weights. Right? Remember, we're going to visualize the weight of the filters. So now we're going to visualize the pre-trained weights that VGG has learned on ImageNet. Okay, and now we see, yeah, interesting patterns. Some of them it's definitely more converged and more clear, right? So this one responds only to red. This one seems to respond, yeah, first of all to, yeah, diagonal lines, sometimes horizontal lines. It also seems to want to do two things, like identify horizontal lines and the color blue. This one is clearly responding to horizontal lines or vertical lines. This one is a bit more complicated, and so on, right? That's the first layer. Second layer gets a bit more pronounced. So here, again, we clearly have diagonal lines in different directions or horizontal lines. We also see more textured values and different combinations of colors. Like this one is very particular, responding to colors like magenta or white or yellow or green. This is responding to diagonal lines, but only if they're like blue or reddish or black, right? And even deeper, we start to see interesting patterns. So these layer 2 already. So by the way, we're not visualizing all the filters of all the layers. We're just going to choose a few that look interesting. Right? And we see that indeed deeper network, we get more interesting patterns. Like here, this one, yeah, it seems to be, yeah, these are, yeah, kind of swirled or bandy lines that they're responding to. Also can be also more wavy lines in the images. This one also more wavy, and again, it responds to this contrast of red or black and white-ish colors. And even deeper, we see circles appearing, so that's what it's responding to. And here as well. Right? And this one responds to more like, yeah, either short horizontal lines or intersections between lines and other lines and so on. Okay. It gets even more interesting if you go deeper in the network. So here we can see it responds to kind of U shapes in the image, or particular other colors, or yeah, these S kind of wavy shapes in the image. Even deeper, we see circles appearing in different colors. Again, these U shapes, or yeah, more rectangular shapes, very clear rectangular shapes that are like a series of shapes, right? and even deeper the deeper we go, the more abstract and, well, uniquely they're responding to certain aspects. Right? Like these are like broad lines no matter what the color is. Here also broad lines in this direction no matter what the color is. Swirls of all kinds of shapes. Yeah, these deep U shapes. These look almost like arches or feather patterns, and so on. You can keep looking at these, and you can always, yeah. It's surprising how particular each filter is responding to really particular input uh, properties, right? Even deeper, we can see kind of waves and patterns, and this looks almost like a landscape of mountains and valleys and so on, right? Or like swirling patterns, exploding patterns, very sharp edges here. These look like almost like eyes. You can see how each of them is, every layer deeper we go, the more peculiar or more distinct and unique the features are, responding to certain things that may occur in certain images and not in others. This is even deeper. And you can also see they start to respond to very, yeah, this almost looks like a cityscape or houses, right? And these look like arches that may occur in different ways in images. These look like close-up eyes, right? It's very interesting to see how these models kind of learn these things. Right. So, bottom line is that these patterns are clearly responding to very particular things in the input image. And by combining all of them, like, by the way, this layer here might have maybe 128 of these guys, right? And each of them responding very particularly to very particular patterns in the image. And by doing that, it becomes very easy then for the last layers to map those to a particular output class. Right? If certain patterns occur, then maybe the image is of a cat or a dog, or if it's something else, then it's a landscape, or something else, then it's a car, something else, then it's a human. Right? And by doing that, the model learns to really identify certain things, and that gives us a much better representation than the input pixels for the model to learn with, right? So remember, at the end of the day, what will happen is that every input image is going to pass through this. And so if we have maybe like 120, maybe it's even 200 more, but say it's 128, this will respond into a vector of 128 values. And it's going to tell me, okay, it's responding by this particular input image. Say it's an image of a cat, right? It may respond to this one, maybe with 0.5 or 0.05. And this filter responds only 0.01. And maybe this filter responds 0.12, right? By having the exact combinations of how each filter responds to this particular input image, that combinations of features will give a much better representation of the input image than the pixel values originally. And each input image now becomes a point in this 128 dimensional space where the cat could be here, other cats are maybe close by, and dogs are maybe over here, right? And houses are somewhere over there, right? Because two images of cats will respond in very similar embedding vectors in the end, right? And hopefully that will bring them close together. And by doing that, these convolutional layers create learned embeddings so that similar images are close together and dissimilar images are further apart. And I really encourage you to try this out. Take a number of images from different classes, feed them to the network, take the embedding vectors, and plot them, for instance, with t-SNE, and you will see how they will beautifully cluster together. Now, that's it for now. In the next lecture, we're going to look at other ways to interpret the models.